Hello friends, in this video let us discuss about the working principle of synchronous motor. So electrical motor in general can be defined as an electromechanical device which converts the energy from electrical domain to mechanical domain. So based on the type of AC input, we have classified the motors into single phase motors as well as three phase motors. So as we are having single phase AC supply and three phase AC supply, we have classified the motor into single phase motors and three phase motors. So now among the single phase motors, we are having single phase induction motor and single phase synchronous motor. Now again if I classify the single phase synchronous motors, so the one motor can be the hysteresis motor and the other is the synchronous reluctance motor. Now among the three phase AC motors, we are having again three phase induction motor as well as three phase synchronous motor. Now in this video let us discuss about the working principle of your three phase synchronous motors. So let us say I am having a three phase windings. So let us say I am having a three phase windings where the space displacement between each two windings is equal to 120 degrees. So let us say the three phase windings are spatially distributed and the space displacement between each two windings is equal, and if I feed these three phase windings with a balanced three phase supply, that means the currents are equally displaced in time domain. So the two conditions to be met for forming a rotating, or you can say the producing a rotating magnetic field, is there should be a balanced phase supply, that means the currents are equally displaced in time domain of equal magnitude and the windings are spatially distributed, that is the space displacement between two windings should be equal, then a rotating magnetic field is produced. Now if I place a electromagnet in this rotating magnetic field and excite this electromagnet with a DC current, then electromagnetic poles will be formed on this electromagnet, and after some time magnetic locking takes place between the electromagnetic poles of this rotor and the rotating magnetic field. Now as the rotating magnetic field rotates at a speed which is known as the synchronous speed, and after some time as magnetic locking takes place between the rotor and the stator rotating magnetic field, then the rotor will also rotate at the same speed as that of the rotating magnetic field which is rotating at synchronous speed. Now the synchronous motor is so called because the rotor of the synchronous motor rotates at the same speed as that of the rotating magnetic field. So hence, for this reason, the synchronous motor is the name of this three phase AC motor is given as the synchronous motor, where the rotor rotates with the same speed as that of the rotating magnetic field. So the synchronous motor is a fixed speed motor. It's a fixed speed motor because it has only one speed, there is no intermediate speed, and the motor rotates in synchronism with the supply frequency. The motor rotates in synchronism with the supply frequency. Now as the supply frequency is constant, the motor behaves as a constant speed motor. Now if you want to change the speed, then definitely you have to change the supply frequency. Now if I change the supply frequency, then only I can able to change my speed of the motor. So now if I say for any rotating magnetic field, the frequency will be proportional to the rotations, or you can say the cycles per second. So if I say the rotating magnetic field is rotating at some speed, let us say that is a synchronous speed, so the frequency is proportional to the synchronous speed, that is the revolutions per second, you can say. Now if I want to convert into minute, then I will divide it by ns by 60. That means the frequency is proportional to ns by 60, that is the revolutions per minute. Now I can replace this proportionality sign with the pole pace. So generally in motors we are referring always pole pace. So I can replace this proportionality with P into ns by 60, and as we are referring the poles as pole pace, therefore I can write it P by 2. Suppose let us say I am having a pole pair, so one pole pair indicates two poles. one pole pair indicates two poles. That means if I write it, P is the number of poles, F is the supply frequency, Ns is the synchronous speed. Now if I put F is equal to 2 here, 2 by 2 into Ns by 60, that means this reduces to 1. Whereas you are having a single pole pair, that is 1. So in this way you can derive the synchronous speed formula, that is Ns is equal to 120 F by P. So where the synchronous speed depends on the frequency as well as the number of poles. Now as long as the supply frequency is constant, the speed of your synchronous motor remains constant. Now if you go to the construction details of the synchronous motor before proceeding to the working principle, so generally the construction of your synchronous motor is similar to that three-phase induction motor. So here you are having the stator. So generally we know that any rotating electrical motor has mainly two parts, one is the stator and other is the rotor. So now if I say the stator again can be divided into three parts. So one is the frame, and other one is the core, and other one is the windings, that is the three-phase windings. So the frame is the outermost part of the synchronous motor which protects the field windings as well as the stator core, and it provides mechanical strength to the inner parts. So the frame is a protective layer of the synchronous motor. Now the core is made up of number of laminations, and the laminations are made up of stampings which are stamped together to form the stator core. Now the laminations are made in order to reduce or in order to minimize the eddy current and hysteresis losses. So if I say the laminations are nothing but the layers, so here is your one stamping, and again you are having others, so this is your other stamping. So these layers are nothing but the laminations. So the laminations are made up of stampings. So stamping is nothing but the forming a metal into a specific shape. So I am stamping, so like this you are having the stator core which are made up of number of laminations, and the laminations are made up of stampings, and they are stamped together to form a stator core. Now inside the periphery of the stator core, so here this is your frame, this is your stator core, and these are your slots. So you can say these are also slots on which the three-phase windings are wound for the same number of poles as that of the rotor. So if the rotor is of two poles for a single pole pair, then the stator should be also wound for a single pole pair. They should be equal. So here are your three-phase windings, and the rotor of synchronous motor is basically of mostly salient pole type. So here we are having an electromagnet, and now the electromagnet is supplied with a DC current. So here we are having DC supply. So the DC supply is provided to the electromagnet via slip rings. So here you are having slip rings. So using the slip rings you are going to supply the DC current. So the function of slip ring is just they convert the stationary supply. Here you are having the stationary part, and here you are having rotating part. So it takes the input from the stationary part and feeds to the rotating part, and vice versa. That is the function of the slip rings. So this is basically the simple construction of the synchronous motor, where we are having stator frame, core, windings, and next the rotor is of electromagnet, or you can also use sometimes permanent magnet also, and the rotor is fed with a DC supply which excites the electromagnet, and electromagnetic poles are formed on this rotor, and now there is a constant flux produced by this rotor because of the DC supply. And now a question may arise in our mind, why we are feeding the rotor with the DC supply only? What happens if I excite my rotor with a AC supply. So basically in synchronous machines, the excitation is nothing but the supply of DC current to the rotor windings to work like a magnet with fixed polarity. So to work like a magnet with fixed polarity, basically excitation is provided. Now that means it will get fixed polarity. As the excitation is provided to the rotor windings, it magnetizes the rotor and the electromagnetic poles are formed on the rotor, that is of fixed polarity. Now instead of DC, if I supply AC, so AC we know alternating current, and when you supply the AC current, so you will be having, suppose for first half cycle, let us say I am having a north pole here, and for the next half cycle I will be having a south pole. So there is no steady magnetic field like in DC supply. Here the electromagnetic poles will always be alternating due to the alternating current. So let us say the supply frequency to be 50 Hz. Now then for 50 times these electromagnetic poles will keep on changing in a synchronous motor if we excite our rotor with the AC supply, and it is undesired effect in the working principle of your synchronous motor. Now if we go to the alternating that is the alternators, then we are not feeding it with the AC supply, because when the rotor spins you will be having the rotating flux and the stator windings will receive the alternating flux which is rotating as well as alternating. So when the AC current is provided to the rotor, so then the electromagnetic poles will be formed on the rotor, and now as this AC current excites the rotor, there will be a flux, and as the rotor spins, the flux will be rotating, and the stator windings will receive this alternating flux, as one is the rotating flux plus that flux is alternating. So this will be difficult for the stator windings to produce a required sinusoidal waveform as output. So hence, for this reason, in synchronous motors and alternators, we are exciting the rotor with DC supply to produce a steady magnetic field instead of the AC supply, which produces the changing electromagnetic poles on the rotor. So now this is the concept behind providing DC excitation. Now moving to the working principle of synchronous motor, your synchronous motor is a doubly fed, or you can say a doubly excited machine. So to the three-phase windings, I am providing a three-phase supply. This is IR, IY, IB. So as the windings are spatially distributed, as we have discussed before, that is the spatial distribution between each two windings is 120 degrees apart, and if the currents, that is a balanced phase supply, you can say the currents which are of equal magnitude are displaced equally in time domain, then a rotating magnetic field is formed. So you can see the stator core carries the alternating flux, or you can say the rotating magnetic field, and if this rotating magnetic field rotates at a speed which is known as the synchronous speed, so hence now the rotating magnetic field rotates with the synchronous speed, and if we see the speed of that synchronous rotating magnetic field, so let us say, considering the two-pole machine, so let us determine, for example, the speed of the synchronously rotating magnetic field. So for considering a two-pole machine of 50 Hz, so by substituting here, I'll get, this is 3000 revolutions per minute, or you can say 50 revolutions, this is per second, this is per minute. This is per second, and 3000 revolutions per minute, and this is 50 revolutions per second. Now let us, so if I say here I am having a north pole and here I am having a south pole on the rotor, and if I say here I am having a north pole, then this will repel. Definitely this will repel, and again for the next second, again you are having here south pole and here north pole, and they will attract. So if we see in detail how this repulsion and attraction occurs, let us move to these two diagrams. So schematic diagrams. So let us say here I am having the north pole of the stator magnetic field, and this is my south pole of the stator magnetic field, and this is the north pole of the rotor, and this is the south pole of the rotor. So let us say the rotating magnetic field is rotating in clockwise direction. So now as they are of the same polarity, so these will be having a anti-clockwise torque on the rotor as they are of same poles. Now as the rotating, or you can say the stator poles are revolving with high speed, that is, for a two pole machine there are 50 revolutions per second. So for the very next second, this north pole will interchange its position with the south pole. So you will get the south pole here and this north pole here for the very next second, and at this very soon the rotor is not able to rotate at the same angle as the stator magnetic field. So therefore again you can see the poles on this rotor as this is north and this is south. So this is basically rotating in clockwise, and again you can see they are of opposite poles, so you will be having the attractive, or you can say the clockwise torque. As they are having opposite poles, they will attract. So this happens. Now why the rotor is not rotating with the same speed as that of the stator magnetic field? Because of the, or you can say due to inertia of the rotor, it is not able to rotate at the same angle as that of the stator magnetic field. Now here we have seen anti-clockwise torque, and here we have seen clockwise torque, and due to the inertia of the rotor it is not able to move in any particular direction, and the rotor remains at standstill condition. Hence for this reason you can say the synchronous motor are not inherently self-starting. Now let us see how can we start this synchronous motor. So basically if I feed some mechanical input here to the rotor, which rotates it in the same direction. So if I say this is my rotating magnetic field which rotates it in the same direction as that of the rotating magnetic field to a speed very close to the synchronous speed, and after some time as this rotor is rotating with a speed which is very close to synchronous speed, the magnetic locking takes place and the synchronous motor rotates in synchronism with the supply frequency. So let us see what are the starting methods of giving this mechanical input to the rotor, and let us discuss the two methods here. So the first method you are having is with the help of external prime mover you can start your synchronous motor. So first one is external prime mover, and the second starting method you can say is with the use of damper windings. So with the help of these two methods we can start our synchronous motor. So let us discuss them one by one. Now discussing about the first method of starting, that is the motor starting with an external prime mover. So here the synchronous motor is coupled with another motor. So the external prime mover, it may be another DC shunt motor, it may be a DC shunt motor or a three-phase induction motor. So here in the motor starting with an external prime mover, the synchronous motor is coupled with another motor. The another motor can be a DC shunt motor or a three-phase induction motor. So by coupling the synchronous motor with any of this motor, it is made to rotate at a speed very close to the synchronous speed. So when it is coupled to some another motor, the DC excitation should be switched off. So initially there should not be any DC excitation and the motor, or you can say the rotor, is made to rotate in the same direction as that of the rotating magnetic field at a speed very close to synchronous speed, and after that you have to provide your DC excitation, and when finally magnetic locking takes place, you have to cut off the external supply to the external motor. So we have to cut the supply to the external motor when the magnetic locking takes place. So this is how you start with the external prime mover. Now moving to the damper windings. So basically the damper windings are the short circuited windings with the help of end rings. The end rings can be made up of aluminum or copper. So generally in case of a salient pole type machine, the additional windings, which are the damper windings, are placed in the rotor pole face. So there will be the relative speed when the rotor is at standstill position. There will be the relative speed between the damper windings which are placed on the rotor pole face and the rotating magnetic field. Now when there is a relative speed, an EMF will get induced in these damper windings, and as they are short circuited, the current starts flowing, and which produces its own flux, and that rotating rotor flux tries to catch the rotating magnetic field as per Lenz's law, and when the speed approaches to near synchronous speed, the EMF induced and the torque reduces. So as it approaches the synchronous speed, the EMF induced in the damper winding and the torque reduces, and when magnetic locking takes place, the torque will completely reduce to 0. So basically with the help of damper windings, you are starting your synchronous motor like just 3-phase induction motor, where we are having the rotor bars are short circuited and the rotating magnetic field is carried in the stator core, and as there is relative speed, the EMF is induced in the rotor bars, and as they are short circuited, you will witness a current in the rotor conductors, and the rotor conductors produces its own flux, rotor flux, and the rotor flux tries to catch the rotating magnetic field as per Lenz's law, and when the rotor flux approaches the near synchronous speed, the EMF and torque starts reducing, and when finally magnetic locking takes place, the torque reduces to 0. So this is basically how you start your synchronous motor, with the help of prime mover and with the help of damper windings. Now discussing about the main features of your synchronous motor. So you can say the first feature is, we have seen the synchronous motors are not inherently self-starting, so they require some external prime mover to rotate the rotor in the same direction of the rotating magnetic field before they are synchronized. So we have seen from these two schematic diagrams, due to the inertia of the rotor is not able to move in any of either directions, either anti-clockwise or clockwise, and your stator poles will rotate at a very large speed, that is the synchronous speed, and the rotor poles are not able to rotate with the same angle as that of the stator poles, and it is because of the inertia. So to basically overcome this inertia, we are using these two starting methods. So now discussing the main features, we have seen it is not self-starting, it is not inherently self-starting motor, and it requires some external means to rotate the rotor in the same direction to the rotating magnetic field to a very near synchronous speed. And the second feature is, the speed of operation is in synchronism with the supply frequency. So here we have seen it is a fixed speed motor because it has only one speed and there is no intermediate speed, as the speed of operation is in synchronism with the supply frequency. Now if you want to change the speed, then definitely you have to change the supply frequency by using some cycloconverters. And the third feature is, the synchronous motor has a unique characteristics of operating under any electrical power factor. So it may be operate at a lagging power factor or a leading power factor or a unity power factor. So this finds advantage of using synchronous motors in power factor improvement in power systems. So basically in power factor improvement, these synchronous motors are used. Now, after discussing these features, let us see the applications. So, the application includes the synchronous motor having no load connected to its shaft can be used in the electrical power factor improvement. Now, owing to its characteristics to behave at any power factor, it finds application in power systems where the static capacitor are expensive. So where the static capacitor gets expensive, you can use your synchronous motors for the electrical power factor improvement in power systems. And the second application is the synchronous motor finds its application where you require low speed, the operation speed is low, where you require low speed but high power. So it finds application where you require low speed but high power. Now, speaking about the power range for 25 kilowatts, let us say 35 kilowatts to 2500 kilowatts, the size, weight and the cost of the 3-phase induction motor is much more compared to your 3-phase synchronous motor. Hence, for this reason, we find the synchronous motor application in this high power range compared to your 3-phase induction motor. Example, you can say the reciprocating machines. So, reciprocating machines or compressors, you can state as the examples. So, this is all about the construction details, working principle, features and starting methods of your synchronous motor. I hope you have understood well. Please subscribe to the channel. Thank you.